uh, we talked about some of the new techniques that are being developed, that have been developed for structural ceramics, and the new techniques that are being used for ceramics now are all based on these techniques that were developed almost about 20 years ago under the Department of the Defense Advanced Research Projects Agency, or DARPA, in the early to mid 90s. So one of the techniques that I developed was based on a technique called extrusion freeform fabrication. So this is based on the standard Stratasys uh, fused deposition modeling. But in order to do that, we had to use a high pressure extruder head that had to be attached to this machine and modified this machine to think that it is actually doing fused deposition modeling while it is actually doing uh, prototyping with ceramic formulations. We also developed a technique called shape deposition manufacturing, and nowadays you will find that there are a lot of techniques that are based on this original technique that was developed by my company Advanced Ceramics Research, Carnegie Mellon University, and Stanford University. In this technique, what we do is we deposit, there are two nozzles. You first deposit a wax material. The first one would be the actual wax itself. After every layer is built, then you go and machine off the hole inside of that, and then you would go and deposit a water soluble UV curable wax inside that mold. Then you would melt away the supporting wax and you get this part, and you can use it as an investment casting mold or whatever. So this would be one way to do it. The other one would be to deposit this material, which is actually water soluble, UV curable, and then you would deposit additional wax on top of that, and then you would just wash away this inside mold material, so you have a very accurate mold. Uh, as I told you, the problems with many of these techniques is that you have, because they are built in layers, you have what are called stair step features. So the edges are not really uniform like you would get in the case of a machined sample. Uh, so by combining the deposition with the machining, or you have an addition step and a subtraction step, a partial subtraction step, and then you would deposit a gel casting slurry into that, a ceramic gel casting slurry into that, and then you would remove this wax mold around it, and then you get this mold material, and you can you can machine off this extra material in the green state itself, and then you would, in the case of ceramics, you have to do what is called binder burnout and sintering, because this slurry contains some binders and things like that. So this is the actual machine. It's actually a machine uh, that is like a lathe, a combined lathe time machining type of head. So it's a combination of additive and subtractive process. It was retrofitted to an existing CNC machine. Right now, the only organization who is doing the shape deposition manufacturing, I'm not really sure if they are still doing it or not, is Professor Fritz Prinz at Stanford University. I don't think that there is anybody else doing this at all. So what did I tell you? I mean, what are the problems with rapid manufacturing? Especially if it is a ceramic, you will have defects in the green parts. Because this is a stair step feature, you have these steps in the part, so it doesn't give you a nice clean finish. So that's the first problem. And the second problem is that you can have subsurface flaws. In the case of metals or in the case of plastics, this may not be a big problem, but in the case of ceramics, these subsurface flaws especially are going to be starting points for failure. So you don't want to do that. So you can do, what you have to do is you have to build in modifications to build strategies so that you do not have any kind of gaps between these places. And this happens mainly because what you're doing is you are putting in the outer perimeter and then you are filling the inside as a raster pattern. That's how most of the build patterns work. So between each of those set of roads, you will have a gap. So you have to avoid that if you have to avoid these gaps. Or what you would do is you would build some excess and then you can machine off the excess area. Not the best way, but it can be done. So we made these things and then we were able to avoid these gaps completely when we built our samples. Of course, we were never able to completely remove these stair-step features, but we were at least able to avoid these subsurface flaws. So here are some examples of rapid manufacturing and unique properties of components that you can get only by using additive manufacturing approaches. So here is a silicon nitride bladed disc for NASA. This has got something like 56 integral blades attached to a solid inner ring. You built it during the actual process itself. So in order to build it, it took us something like 64 hours, 64 to 96 hours it took us. So, and it was done non-stop, almost non-stop. Then you had to debind it, which took us another 96 hours, and then sintering, which took us something like another 72 hours. And this was the first biggest ceramic piece ever built. This was approximately 8 inches long. But now people are making more bigger samples now, but we were the first ones to do that at that time. And the other thing that we did at my previous place of employment was, because the fused deposition modeling needed some kind of support material at points where there are undercuts and overhangs and things like that. And we developed a water soluble material that could be deposited with a second nozzle. And this is the actual part itself, and then you can just wash out with cold water, cold tap water. And this product won the R&D 100 award for my old company in 1999. And this is the actual sample itself. So you could make some really complicated shapes, and you can just wash out this support material with plain tap water. So this was a great way to do that. The other one is we made some what are called ceramic heat exchangers. So in If you want to remove the heat from a high speed electronic structure, you know about the amount of heat that comes off of your laptop, but you don't have any kind of liquid cooling in there. I mean, there are only two laptops that operate by liquid cooling. One is by Fujitsu, and the other one, I believe, Lenovo or somebody like that. And I don't believe that they tried that in about 10 years ago, but afterwards they never they stopped building those kinds of laptops. But um, there are a lot of applications where you generate a lot of heat and it needs to be removed in a very short time. So in order to do that, you have to have some kind of a liquid cooling. So here is a solid piece. The advantage is that this ceramic material closely matches the coefficient of thermal expansion of silicon or versus some of the newer materials like gallium nitride or aluminum nitride and things like that. By removing this, by using some kind of a liquid coolant in that, you can remove up to 500 to 1000 kilowatts per centimeter squared. So you remove that much heat. Okay, so and you can see this in the actual performance of a representative sample. So when we did that, um, you can this is the typical high performance air cooled heat sink. So you can only get this is in terms of thermal resistance. You need to have as low a thermal resistance as possible, like uh, zero point 0.1 to zero point 0.2. If you increase the amount of liquid coolant that is flowing through these channels, you can get very low thermal resistance. The problem with copper is that its CTE does not match that of the new high-speed devices, like um, based on gallium nitride and uh, aluminum nitride and so on, gallium arsenide and so on. So that's the advantage of something like silicon carbide. Some of the advantages is that if you have small fibers like nanoparticles, if you are extruding them through a nozzle, you can align them and they would just all coagulate together to make it into a fiber. The advantage is that if you extrude it, you get preferential strengthening of these fibers in a particular direction. One of the things that I did a couple of years ago was that you heard about different kinds of implants. The most common implant is made out of titanium or stainless steel. What is the disadvantage with the metal, those kinds of metals? The problem is that those metals are much stronger and harder than our natural bone, and they do not have the same inner structure like our bone. So what they can do is they can break off small pieces of our bone during the time it is implanted into our body, and it can break away and chip away. So if you have an implant today, after about 10 to 15 years, you will have to go for a revision surgery and put in a bigger implant into that same place. But if you had a material that is a combination of a plastic and a ceramic, the ceramic helps to generate the body's own natural bone, over a period of time, and it can be built using 3D printing, because all you have to do is you have to do an MRI scan of your broken area, and then if it is on the, so you do the MRI scan of the good bone, and then you reverse it, and then you build the implant for this particular area. It is porous, and it has got the same structure as our own body's bone. Or it can be a uh, traditional log pile type of a structure, and then the body will grow its own natural bone. Over a period of time, this plastic will get eaten up by the body and then get completely replaced by the body's own natural bone. So that's the whole idea. I mean, when we did that, nobody believed us. So you can see the how the body's own natural bone is grown into those porous areas, and this plastic will take a long time for it uh, to be removed by the body. So over a period of time, your body will grow its own bone. When we did that, nobody believed us, but now everybody swears by this. And we didn't continue it further because we had a really tough time to get this patented. But that's what everybody is doing now. So you can see, I mean, so these are some of the properties of the, and how it is built and things like that. I won't go over too much into that. So you can see that how the bone grows its own. So this is the old bone, and this is the new bone that is generated by the body. So over a period of time, the body grows its own bone. The other one is how you can align fibers or fibrils in an extruded part. So if you have nice orientation of those fibrils, you can strengthen any kind of material. So by extruding it in a certain through a nozzle, you can align the fibers, and it increases the strength of your part that you are producing. So if you have up to 20-25% fiber that is added into a resin, by extruding it through a nozzle, you can strengthen this composite material. So that cannot be done by any other way other than by rapid prototyping or 3D printing. So this one gives you some additional properties of that. Something that happened about 20 plus years ago, maybe in the mid 90s to late 90s, was a project funded by DARPA, and they called it MICE. MICE is mesoscopic integrated conformal electronics. So you can build an actual electronic structure from a CAD model. For example, in this. So if you want to build all these things from scratch, so this was a GPS system built on the MICE program right from scratch, and it worked. So suppose you're somewhere you don't have any access to anything, and if you have a 3D printer, you can build your own electronic structure. That was the whole idea. For example, if the soldiers are doing something and they have access to a 3D printer, a portable 3D printer, they can build it right then and there. Um, you could also do like reshuffling genes, so depositing genes in uh, in portable wells and things like that, so you can generate your own types of cells that are compatible with your body. So you can do that using 3D printing. That's the idea. I don't think that it is true yet, but it can be done. The more um, recent development that is being used by people like GE to make their new Gen X engine is a technique called laser engineered net shaping. It's a direct metal rapid prototyping system that allows for near net shape fabrication of different materials such as stainless steel, um, tool steels, Inconels, titanium Ti64, and nowadays several high temperature nickel superalloys are being made using this laser engineered net shaping, and it has been licensed to a company called Optomec, and they are building that, and we are in the process of buying a new machine at OSU based on the Optomec technology. So how does this do that? So you have a laser and you have a nozzle where you're spraying this powder. I think the next one, I don't know if I have that, but and then you sinter those particles together and build the whole part. If you want to make a part that is about 1 foot in diameter, 1 foot in 1 foot cubed in volume, you can build this whole part, say, in a couple of days. But if you wanted to make a part like this using traditional machining and things like that, it will take you many days, many weeks, and things like that. But the other interesting thing was that these materials that we built demonstrated better strength properties than the parts that were built using traditional methods, and that is because of uh, the way these materials are built. Because I mean, if you did using lens, you had a yield strength of 58 ksi and ultimate strength of 120 ksi. Compare that with wrought material. So why do you get an improvement over the traditional methods? And that is because of the way the part is built. So if you build it using the traditional methods, you have a very non-uniform structure. But if you build it using 3D printing, you are building things in a directional manner. So you are aligning these grains in a certain direction that allows you to get better properties in specific directions. Okay, so this one is the traditional alloy, and the earlier one is um, the part that is built using 3D printing. So that gives you better properties. What do you think will happen in the future? I mean, I think it has already happened, which is that 3D printing is being used for actual manufacturing itself. So this is what we predicted about 20 years ago, which will happen. And now we are thinking that people are already taking these ideas and running with them. And I believe that um, you can use that to make um, niche products at the same cost of making 1,000 parts. Okay, so this one is the homework. So I'm thinking that you have already uh, done that, but please make sure that you are meeting that. I will set up a homework Dropbox, so please respond to that accordingly. Okay.